Hello, this is Douglas Groom from Geometrics, Inc., a manufacturer of geophysical exploration instruments. Welcome to the Groundwater Survey. And we are going to talk today about using electromagnetic EM instruments for groundwater exploration. And the particular techniques we're going to be talking about today are variations of the magnetotelluric method, and we are going to be explaining AMT, which is audio magnetotellurics, HSAMT, which is hybrid source magnetotellurics, and CSAMT, which is controlled source magnetotellurics. As near surface groundwater resources become increasingly polluted and depleted, there is a greater demand for deep aquifers. And in many areas, these aquifers are at 200, 500 meters, a kilometer meter, and sometimes even greater. And special geophysical instruments are required in order to properly map these aquifer groundwater resources. And the use of geophysical tools for groundwater exploration allows the hydrologist, geologist, geophysicist to get a map of that subsurface geology. And that geology can be interpreted into the hydrogeologic structure of the subsurface. Now, the audio magnetotelluric method, AMT, is typically used for groundwater exploration, minerals exploration, shallow oil and gas, geothermal reservoir mapping, deep geotechnical and engineering applications, and academic research and teaching. So, what do these methods do? They create a series of resistivity maps to depth and for a 2D survey along a profile. So you get depth and profile, which is essentially a slice into the earth. And these resistivity maps, as mentioned, are related to the geologic structure, which is interpreted as the hydrogeologic structure. And what I'd like to do now is show a few examples of how these methods are used and interpreted for groundwater exploration. This is an example of a groundwater survey done in coastal California. Coastal California is typically marine sediments, and the groundwater aquifer are typically sand and gravel channels. These are ancient stream beds, also known as paleochannels, that have been etched into the underlying sediments and then overlain with other marine sediments later. These marine sediments are heavily clay and silted content, which tend to be electrically conductive. The sand and gravel channels tend to be electrically conductive, resistive. So we are looking for a resistor sandwiched between two more conductive layers. And what we see here are a number of changes in the geologic horizon. These are known, this is the base of the alluvium. This is another known geologic structure, but we see here a more resistive area that goes to depth. Unfortunately, this is only a 2-color scale, so it doesn't bring out all of the detail. But what we're looking for is a resistor sandwiched between conductive layers. That's what we see. A well was drilled here and it was productive. This is an example of a number of lines of a survey, and we're just going to look at one section of this. And what you notice here is, especially between stations 13 and 14, you have a very sharp, well-defined contrast here. This, by the way, was a survey done with the stratagem by a company called Hasbrook Geophysics, and we thank them for the cooperation. We see this sharp contrast, which was interpreted as a fault very often. Groundwater is found in these faulted and fractured zones. A well was drilled here, just south of this boundary. And what we see, that this water well was drilled at 90 meters depth, and it produced 600 gallons per minute, which very much changed the water situation in this area of Haiti. This was a very deep survey, looking down at nearly 1.5 kilometers, and we see this is a karstic environment. We have this underlying basement, and the overburden is quite deep, but we see etched into the basement are these number of areas here. These are interpreted as being faulted areas. A well was drilled in the deeper area, and turned out to be the most productive well in this area, this desert area of northern China. This was not specifically a groundwater exploration. This was a fault mapping survey done in Japan, but I wanted to include this because this area here is very clearly a fault. There is no surface expression here. There is overlying sediments down to about 40 or 50 meters here, but this is clearly a fault zone and probably a slip fault based on the orientation of the fault and the offset of the geology. It was not drilled because it was not a groundwater survey. This was another survey done in Japan using the CSAMT method, and these areas here, again, were interpreted as faults. They were not drilled, but the recommendation would have been to drill in these more conductive, weathered, faulted areas. These last two were done with the Geode EM. This was another one done with the older version of the AMT instrument, the stratagem. And again, we have a very marked interface here. And between stations 9 and 10, it's very difficult to read that, but this is 9 and 10 here. There was a well drilled here, produced 350 gallons per minute, and the application was actually for a mining operation, but the mining operation needed water for its processing, and the local water was not sufficient. This new well provided sufficient water for those operations. This is another groundwater survey done in Nevada, in the United States, and basically this is a number of different lines that were done at this mining operation, looking for the water. This is the section that we looked at previously. And by doing a number of different lines, they focused in on the area that was the most likely to be productive as a well. This was another one done with the Geode EM. This was actually in a public parkland, so we were not allowed to drill. And we can see that there are two resistive layers here. There is a relatively conductive layer through there. It needs further interpretation because we have really no ground truth here. The sediments down to about 50 meters are more conductive deposits. There's a resistive layer here, another conductor, another resistor. Obviously sedimentary layers, probably marine and maybe more sands and gravels in this area. We do not have ground truth, and it's a short survey, only about 400 to 500 meters long, and we're looking at a depth of about 1,000 meters. So what does this instrument do? The process data provides a map of the 2D and 3D structures of the subsurface geology down to a depth of kilometer and more depending on the structure of that environment. And as mentioned, these geoelectrical structures are related to the geologic structures which can be interpreted for the groundwater resources. For those of you who are familiar with the various techniques, this particular instrument is a 6-channel instrument, and we are measuring both electric and magnetic fields. And as the data is being collected, we can see the 6 electric channels, the 2 magnetic channels, which is the setup in this case. And the thing that is causing these signals are lightning strikes in the atmosphere. And these lightning strikes can be very distant. They can be hundreds, even thousands of kilometers away. And we're seeing on these events in the time series. This is time, and this is the amplitude in each one of those channels. These events are distant lightning strikes. And again, they could be hundreds, even 1,000 or more kilometers away. And for those of you who are familiar with resistivity surveys, typically you will see an apparent resistivity versus some measurement of depth parameter. In this technique, we use frequency to determine depth. That will be explained in more detail later. And this is an example of 4 soundings that were all done simultaneously. Each receiver box is doing 2 soundings and in 2 directions each one. The red curve is along the profile line, and the blue curve is perpendicular to the line. So we actually are having 8 soundings done simultaneously here. And that's the first box, that's the second box, and a very nice resistivity curves here. In the magnetotelluric technique, the phase of these signals are also very important. So we do display the phases again in the X and Y direction. And we also display a resistivity and depth curve. And for those of you familiar with borehole hogging of resistivity or standard resistivity surveys, these curves are very familiar to you. And because we are making 2 measurements at the same time in each direction, we have along the profile and perpendicular profile, which allows us to get a more accurate view of the true ground resistivity. And the thing that I want to highlight here is in this particular survey, we're looking down, that's 1,000 meters right here, and that's 2,000 meters. And we're getting good data down to 1,000 meters. We're getting a lot of scatter beyond that. That was because we were using stakes instead of porous pots. But we do have very good data down to about 1,000 meters. So what are these techniques? What is AMT, HSAMT, and CSAMT? The techniques, as I mentioned, these are variations of the MT magnetotelluric, which is a frequency domain. And in the frequency domain, we are using many different frequencies that are from currents that are naturally flowing in the ground. And these natural flowing currents are caused by typically distant lightning strikes in the AMT band. And they create currents flowing in the ground, and these currents create both electric and magnetic fields. And by measuring these fields, we can get a ground resistivity. However, in that AMT band, there is a band of frequencies that is typically very weak. So what we do is add a small, portable, low-power transmitter that runs on a standard 12-volt car battery to enhance those weak signals. The other technique is controlled source AMT. It does not use natural fields at all. It uses only a man-made transmitter. This is a very large, very powerful transmitter, up to 30, even 40 or 50 kilowatts. So, how does this work? There are electric currents flowing in the earth. They are caused by lightning strikes, typically. These electromagnetic waves are coupled from the atmosphere into the ground by electromagnetic induction. These are actually what's called displacement currents. The current flowing in the ground generates an electric and a magnetic field. And the ratios of the amplitudes of these natural electric and magnetic fields can be used to calculate ground resistivity. And by looking at different frequencies, we get ground resistivity at different depths. So the hybrid source techniques is used to enhance that that natural field in that natural field weak signal area, also known as the dead zone, and that's typically between 1,000 to 4,000 hertz. This is the transmitter that's used. There are 2 induction loops, runs on a typical 12-volt car battery or marine deep cycle battery. And this on the Geode EM is an option that can be added on, and it basically generates frequencies for a little over 1 kilohertz to 16 kilohertz. This is an example where this transmitter was very useful. As you can see, we have very nice data down to less than 1 hertz here. But in the dead zone area, between 1 to 3 kilohertz in the X, which is the red direction, we have good data. But in the perpendicular direction to the survey, the signal is so weak that in that band, that signal is unusable in all 3 of these soundings that were done at the same time. So what we did is we ran the transmitter for 10 minutes to see if we could improve that signal in that area, and that's what we got. It dramatically improved the Y direction and improved the X direction in that AMT dead zone. CSAMT is a very different technique that only uses controlled source transmitter. As a matter of fact, the natural sources are a noise source in this technique. They're not used. When would you use CSAMT? Typically, it's only used when there is very strong cultural noise environment that you must deal with on that particular survey site. This could be something like a maglev train working in a urban industrial area with very strong cultural noise, working in an active oil field where there are lots of pumps, or working in a mining site where you've got a 20,000 volt smelter acting, and you need to do a survey in that area. So these natural fields are overwhelmed by the cultural noise, and very often CSAMT can have a powerful enough signal that you get maybe not the best but usable measurements. However, there are disadvantages of CSAMT. The transmitters are expensive. You can easily spend well over $100,000 only for the transmitter. They can be dangerous. You need a very knowledgeable operator because we're dealing with 1,000 volts we're putting into the ground at 10, 20, 30 amps. Typically, these transmitters will have a very large dipole, anywhere from 1 kilometer to 2 kilometers in length. And you need to find a site that's 5, 10, 15 kilometers away from your survey area that you can put up these long dipoles parallel to your survey line. And if you're doing a tensor survey, parallel and perpendicular to your survey line. So that requires at least another 3 people, a knowledgeable transmitter operator and at least 2 people to guard the dipoles against local people getting into that area and trying to dig up maybe the cables. You don't want to do that if you're putting 1,000 volts at 20 amps into the ground. Okay. This is an example of a CSAMT survey done with the Geode EM, and this was to quite a great depth. We're looking down to all the way down to a 10-second or 0.1 hertz period. Very nice data that matches the phase quite well. And this was a transmitter that was used. This happened to be a 30 kilowatt. Each one of these modules is a 10 kilowatt power supply. These power supplies are feeding into a switcher that generates the frequencies that we're using, and the switcher is connected to the dipoles that are putting that current into the ground. And as a power source, we were simply using an off-the-shelf motor generator. That I believe is a 15 kilowatt motor generator, so we were using actually 2 at the same time. And the layout is very straightforward. There is the receiver box. There's a 12 volt battery to run it. These cables are running to the magnetic sensors. The yellow cables are running to the electric stakes. In this case, we're using a metal stake in the ground. You can use either metal stakes or chemical electrodes called corner spot electrodes. This is another example of laying out the dipole cables. And typically, you can get to 1,000 meters of depth with a simple 50 meter dipole. You don't need a large dipole as you would in a traditional resistivity, galvanic resistivity measurement. In order to get 500 meters with a traditional stakes in the ground resistivity meter, you need to have at least a 2 kilometer long line. Whereas this, you can get to those depths with a simple 50 meter long dipole. This is the magnetic sensor, and they are orienting that sensor, and that happens to be a carpenter's level in order to level the sensor, because you're measuring horizontal fields. And he's using a standard Brunton compass to do that. And that is the box. That is the receiver. And this is more work in the field, literally. This is a cornfield in Indonesia. And thank you for your attention. You can contact me at this email, doug@geometrics.com, and our website is geometrics.com. And thank you. I hope to be available after the seminar, and I would be happy to answer any questions, either directly or through email. Thank you.